Imagine for a moment that you could shrink yourself down to the smallest possible scale in the universe. You pass through atoms, dive between electrons and nuclei, and keep going smaller, smaller, until you reach a distance so tiny that a grain of sand compared to the entire observable universe is roughly the same as this microscopic realm compared to that grain of sand. At this unimaginable scale, something extraordinary happens. The very fabric of reality, the stage upon which all existence plays out, begins to dissolve. Space and time themselves start to break apart, replaced by something far stranger. This is the Planck scale, and it's where our understanding of physics doesn't just get complicated, it completely shatters. Welcome back to another gentle exploration of the universe's deepest mysteries. I'm here to guide you through one of the most profound questions in all of science. At what point does the smooth fabric of space-time give way to the bizarre quantum world? Tonight we'll drift together through dimensions so small they challenge the very meaning of existence itself, where the laws that govern our everyday reality simply stop working. If you've ever wondered whether there's a fundamental limit to how finely we can divide reality, or if you've pondered what might lie beneath the surface of space and time, then settle in. We're about to embark on a journey to the very edge of the knowable universe, where physics meets philosophy, and where the answers we find might just change everything we thought we understood about the nature of existence. Let's begin with something that might surprise you. The space around you right now, the seemingly empty void between your body and the wall, between the Earth and the stars, isn't empty at all. It's not just filled with invisible particles or fields, though it is that too. More fundamentally, this space is something. It has properties, structure, and behaviour. It can bend, twist, ripple, and even tear. This revelation came to us through Albert Einstein's general relativity over a century ago. Yet it still feels almost mystical when you really contemplate it. Picture space-time as a vast invisible fabric stretched across all of existence. This fabric responds to everything placed upon it. A bowling ball creates a deep depression. A marble makes a gentle dimple. The planets in our solar system roll along the curves created by our sun's immense mass, and we call this rolling motion gravity. It's not that objects are pulled toward each other through some mysterious force. Rather, they're simply following the straightest possible paths through curved space-time. But here's where things become interesting in a way that will set the stage for everything that follows. This fabric, this foundation of reality itself, appears smooth and continuous from our everyday perspective. You can move from here to there without jumping across gaps. Time flows steadily forward without skipping beats. The mathematical language we use to describe space-time treats it as infinitely divisible, meaning you can always imagine cutting any distance in half, then in half again, forever. Yet quantum mechanics, that other pillar of modern physics, whispers something entirely different. It tells us that at the smallest scales, everything becomes granular, discrete, uncertain. Energy comes in packets called quanta. Matter exhibits wave-like properties that dissolve our classical notion of definite position and momentum. The act of observation itself changes the very thing being observed. These two descriptions of reality, general relativity and quantum mechanics, are both extraordinarily successful within their own domains. General relativity governs the dance of galaxies, the collision of black holes, the expansion of the universe itself. Quantum mechanics explains the behaviour of atoms, the operation of computers, the fusion processes that light the stars. Each theory has been tested to remarkable precision and has never failed within its realm of applicability, and yet they are fundamentally incompatible. The incompatibility isn't just a minor technical disagreement between physicists. It represents a profound crisis in our understanding of reality. General relativity describes gravity as the curvature of a smooth, continuous space-time. Quantum mechanics describes the other three fundamental forces through the exchange of discrete particles in a fixed background space-time. When we try to apply quantum principles to gravity itself, or when we consider situations where both quantum effects and gravitational effects become important, our mathematical frameworks break down completely. The equations literally produce infinite answers, meaningless results that tell us our theories have reached their limits. This breakdown doesn't happen in some abstract mathematical realm removed from physical reality. There are real situations in our universe where both quantum effects and gravitational effects should be important simultaneously. The centers of black holes, where matter is crushed to infinite density according to general relativity, yet where quantum effects should certainly dominate. The first moments after the Big Bang, when the entire observable universe was compressed into a region smaller than an atom, where space-time curvature was extreme, yet quantum fluctuations must have been enormous. These aren't just theoretical curiosities. They're telling us something profound about the nature of reality at its most fundamental level. As we venture deeper into this mystery, we encounter one of the most important numbers in all of physics, though it's so small that it defies intuitive comprehension. The Planck length is approximately 10 to the minus 33 centimeters. To put this in perspective, if you were to magnify an atom to the size of the observable universe, the Planck length would still be smaller than an atom. This isn't just an arbitrary small distance that physicists happen to calculate. The Planck length emerges naturally when you combine the fundamental constants of nature: the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant. It represents the scale at which the uncertainty principle of quantum mechanics begins to affect the geometry of space-time itself. At distances smaller than the Planck length, our conventional notions of space and time become meaningless. Not difficult to understand, not approximate, but genuinely meaningless. The smooth fabric of space-time that Einstein described gives way to what physicists sometimes call quantum foam, a seething, bubbling uncertainty where the very concepts of distance and duration lose their definition. Think about what this means for a moment. Take a breath and consider the implications. We're not talking about reaching the limit of our measuring instruments or our mathematical techniques. We're approaching the limit of meaning itself for space and time. At the Planck scale, quantum fluctuations become so intense that they can spontaneously create and destroy tiny virtual black holes in timeframes so brief they last only for Planck time, about 10 to the minus 43 seconds. These aren't black holes as we normally think of them, massive stellar corpses that trap light for eons. These are microscopic distortions in the fabric of reality that pop into existence and vanish faster than any physical process we can imagine. The energy required to probe distances shorter than the Planck length would be so enormous that it would immediately collapse into a black hole, making the measurement impossible in principle. This isn't a technological limitation we might someday overcome with better instruments. It's a fundamental barrier built into the structure of reality itself. Yet this breakdown of classical space-time at the Planck scale isn't necessarily a problem to be solved. It might be a clue, a signpost pointing toward a deeper truth about the nature of existence. Let's pause for a moment and consider something familiar that might help us understand this transition from smooth to granular. Think about a photograph displayed on your computer screen. From a comfortable viewing distance, the image appears smooth and continuous. Colours blend seamlessly into one another. Curves appear perfectly rounded, and there's no hint of the underlying structure. But as you lean closer to the screen, something interesting happens. The smooth image begins to reveal its true nature. You start to see individual pixels, discrete squares of colour that combine to create the illusion of continuity. Zoom in far enough, and the smooth photograph dissolves entirely into a grid of separate, distinct elements. This analogy, while imperfect, gives us a way to think about what might happen to space-time at the Planck scale. What appears smooth and continuous at the scales we experience might actually be composed of something more fundamental, something discrete and granular. But here's where the analogy breaks down in a fascinating way. Unlike pixels on a screen, which exist within the larger framework of the screen itself, the pixels of space-time, if they exist, would be space-time. There would be no background stage for them to exist upon. They would be the stage itself, emerging from some deeper, non-spatial, non-temporal reality. This idea challenges one of our most basic assumptions about existence. We're so accustomed to thinking of space as the arena in which things happen, and time as the dimension along which events unfold, that it's difficult to imagine reality without them. Yet if space-time truly breaks down at the Planck scale, we're forced to consider what might lie beneath. Some theories suggest that space-time might emerge from something even more fundamental: quantum information. In this view, the bits and bytes of reality aren't matter and energy, but information itself. Space and time, rather than being the foundation of reality, become properties that emerge when information is organized and processed in particular ways. Other approaches propose that space-time is composed of discrete, indivisible units, like atoms of geometry itself. These geometric atoms wouldn't be made of anything smaller. They would be the smallest possible pieces of existence, combining and recombining to create the illusion of smooth space-time at larger scales. As you listen to these ideas, notice how they challenge your intuitive sense of what reality should be like. We're approaching concepts that stretch far beyond our everyday experience, yet they emerge from careful mathematical analysis of our most fundamental theories. The search for a theory that unifies quantum mechanics and general relativity has consumed some of the brightest minds in physics for nearly a century. This isn't just an academic exercise in mathematical elegance. It's a quest to understand the deepest nature of reality itself. One of the earliest attempts to grapple with quantum space-time was the Wheeler-DeWitt equation, formulated in the 1960s by John Wheeler and Bryce DeWitt. This equation represents an attempt to apply the mathematical framework of quantum mechanics directly to the geometry of space-time itself. Instead of describing the probability of finding a particle at a particular location, the Wheeler-DeWitt equation describes the probability of finding the universe in a particular geometric configuration. The equation is elegant in its ambition, yet strange and problematic in its implications. It treats the entire universe as a single quantum system, with no external clock to mark the passage of time. In the Wheeler-DeWitt formulation, time itself emerges from the quantum evolution of spatial geometry. This creates what physicists call the problem of time in quantum gravity. How can we describe change and evolution when time itself is part of what's changing and evolving? Despite these conceptual challenges, the Wheeler-DeWitt equation opened the door to thinking about space-time as fundamentally quantum mechanical. It suggested that the smooth fabric of Einstein's space-time might be an approximation, valid only at large scales, while the true nature of space and time is quantum mechanical through and through. More recent approaches have taken this insight in various directions. Loop quantum gravity, developed primarily by Carlo Rovelli, Lee Smolin and others, proposes that space-time has a discrete structure at the Planck scale. In this theory, space is composed of tiny loops and nodes, like a vast three-dimensional fabric woven from quantum threads. When you zoom in far enough, the smooth curves of general relativity give way to a granular structure of quantum geometry. The mathematics of loop quantum gravity predicts that area and volume come in discrete units, like the rungs of a ladder rather than the smooth slope of a ramp. A black hole's surface area, according to this theory, is composed of a finite number of discrete units, each contributing a specific amount to the hole's entropy. This discreteness of area and volume represents a radical departure from classical geometry, where these quantities can vary continuously. Meanwhile, string theory takes a different approach entirely. Rather than trying to quantize space-time directly, string theory proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. These strings exist in a higher dimensional space-time, and what we perceive as our three-dimensional space plus time emerges as a lower dimensional slice or brain within this larger structure. In some versions of string theory, particularly those incorporating the holographic principle, our entire three-dimensional reality might be encoded on a two-dimensional boundary, like information stored on the surface of a hologram. This suggests that the space-time we experience might not be fundamental at all, but rather an emergent property of information processing occurring on a distant two-dimensional surface. Take a moment to consider how radical this suggestion is. Everything you experience, every object you touch, every thought you think, might be a three-dimensional projection of information encoded on a two-dimensional boundary that you can never directly access or observe. As our understanding of quantum gravity has evolved, a surprising theme has emerged: the deep connection between information and geometry. This connection was first glimpsed in the study of black holes, those regions of space-time where gravity is so strong that nothing, not even light, can escape. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black. They emit a faint radiation due to quantum effects near their event horizons. This Hawking radiation carries energy away from the black hole, causing it to slowly evaporate over time. But here's the puzzle: the radiation appears to be completely random, carrying no information about what fell into the black hole. This created what's known as the information paradox. Quantum mechanics insists that information is always conserved. It might be scrambled, encoded, or transformed, but it can never be truly destroyed. Yet Hawking's original calculation suggested that when a black hole evaporates completely, all the information about what fell into it would be lost forever. This paradox has driven decades of research into the nature of black holes and quantum gravity. The most promising resolution comes from the holographic principle, which suggests that all the information that appears to fall into a black hole is actually encoded on its two-dimensional surface. From this perspective, information never actually enters the black hole's interior. Instead, it becomes part of a complex quantum code written on the event horizon. This insight has profound implications for our understanding of space-time more generally. If the three-dimensional interior of a black hole can be fully described by information on its two-dimensional surface, perhaps our entire three-dimensional universe can be understood as emerging from information encoded on some distant boundary. The mathematics supporting this idea comes from the ADS/CFT correspondence, a remarkable duality discovered in string theory. This correspondence shows that certain theories of quantum gravity in a curved spacetime are mathematically equivalent to quantum field theories, without gravity living on the boundary of that spacetime. The curved interior and the flat boundary contain exactly the same information, just encoded in different ways. This suggests something profound about the nature of space itself. Rather than space being a fundamental arena in which things happen, space might emerge from the entanglement patterns of quantum information. When quantum bits become entangled in particular ways, they might spontaneously generate the geometric relationships we interpret as spatial distance and temporal duration. Recent research has pushed this idea even further. Some physicists now propose that space-time emerges from quantum error correction, the same principle that allows quantum computers to maintain coherent information despite noise and interference. In this view, the smooth geometry of Einstein's spacetime is like an error-corrected code, with quantum entanglement serving as the error correction mechanism that maintains spatial and temporal relationships. As we contemplate these ideas, we're approaching something that feels almost mystical, yet emerges from rigorous mathematical analysis. The possibility that space and time, the most basic features of our experienced reality, might not be fundamental but emergent properties of something deeper and more abstract. The journey we've begun tonight takes us to the very edge of human knowledge, where physics meets philosophy and where our most basic assumptions about reality start to dissolve. We've seen how the smooth fabric of space-time begins to break down at the Planck scale, where quantum effects become so strong that space and time themselves lose their classical meaning. But this is only the beginning of our exploration. In the next part of this journey, we'll dive deeper into the specific mechanisms by which space-time might emerge from quantum information, explore the experimental efforts to detect quantum properties of space-time, and grapple with the profound implications of living in a universe where space and time might not be fundamental at all. Until then, let your mind wander through these possibilities. Imagine what it might mean for consciousness, for existence itself, if the stage upon which all reality plays out is itself an emergent phenomenon, arising from deeper patterns of information and entanglement. And if you're curious about how quantum mechanics might connect to the deepest aspects of consciousness and reality, I invite you to explore our previous journey. Can quantum entanglement unlock a hidden power in your mind? Where we explored the mysterious connections between quantum physics and the nature of awareness itself. Sleep well and dream of quantum foam. As we drift deeper into the mystery of quantum space-time, you might wonder whether these ideas remain forever locked in the realm of pure theory, accessible only through abstract mathematics and philosophical speculation. But something remarkable has been happening in laboratories around the world. Scientists have begun the seemingly impossible task of probing the quantum nature of space-time itself. Picture, if you will, the most sensitive instruments ever constructed by human beings. Detectors so precise they can measure distortions in space smaller than 1,000th the width of a proton. These are the gravitational wave observatories like LIGO and Virgo, originally built to detect ripples in space-time created by colliding black holes and neutron stars. Yet these same instruments are beginning to push against the fundamental limits imposed by quantum mechanics. When you try to measure the position of LIGO's mirrors with extraordinary precision, quantum uncertainty begins to interfere with the measurement itself. The very photons used to monitor the mirror positions carry enough momentum to slightly disturb the mirrors, creating a quantum noise that sets a fundamental limit on how precisely we can detect gravitational waves. This isn't a technical flaw to be engineered away. It's a direct encounter with the quantum nature of spacetime measurement. Even more intriguingly, some physicists have proposed using these gravitational wave detectors to search for evidence of spacetime discreteness. If space is truly granular at the Planck scale, gravitational waves might carry subtle signatures of this graininess, tiny fluctuations that could be detected by sufficiently sensitive instruments. Other experiments take a different approach entirely. At Fermilab, scientists have constructed a device called the holometer, designed to detect the quantum jitter of spacetime itself. The idea is elegantly simple, yet profound in its implications. If spacetime has a discrete structure at the Planck scale, then precise measurements of position and time should reveal tiny, random fluctuations. These fluctuations wouldn't be due to external noise or instrumental imperfections. They would be intrinsic properties of space and time themselves. The holometer consists of 2 laser interferometers, each capable of measuring distances to extraordinary precision. If space-time is smooth and continuous down to arbitrarily small scales, the 2 interferometers should give perfectly correlated results. But if space has a granular structure, there should be subtle correlations between the measurements that reflect the underlying discreteness of geometry. As you contemplate these experiments, notice how they represent a profound shift in our relationship with reality. We're no longer content to theorize about the nature of space and time. We're actively probing the foundations of existence itself. The results so far have been intriguing, but not yet definitive. The holometer has not detected the specific type of quantum noise that would confirm a discrete structure to space-time. Yet this negative result is itself valuable, ruling out certain models of quantum gravity and pushing the boundaries of others. Meanwhile, astronomical observations have provided their own surprises. Some of the most distant gamma-ray bursts, light that has travelled across billions of light-years of space, show no evidence of the quantum fluctuations that certain theories predict should accumulate over such vast distances. This observation has ruled out some models of quantum gravity while leaving others intact. Let's pause for a moment and consider something beautiful about the nature of scientific discovery. Often, when we probe the foundations of reality, we don't find what we expected. Instead, we discover something far more elegant and surprising than our original theories predicted. This seems to be happening with our understanding of space-time emergence. Rather than finding that space and time simply break down at small scales, we're discovering that they might emerge from something far more abstract and beautiful: the patterns of quantum entanglement themselves. Imagine for a moment a vast network of quantum information, spread throughout a realm that has no spatial or temporal structure. Within this network, certain patterns of entanglement begin to form. These patterns don't exist in space because space doesn't exist yet. They exist in a more abstract realm of pure information and correlation. Now, here's where the magic happens. As these entanglement patterns become more complex and structured, they begin to give rise to something we recognize as geometric relationships. Distance emerges not as a fundamental property of space, but as a measure of how strongly different parts of the quantum network are entangled with each other. This idea, while still speculative, has found remarkable support in the mathematics of string theory and the holographic principle. Calculations show that when quantum systems become entangled in specific ways, the pattern of their entanglement naturally gives rise to curved spacetime geometry. The more entangled two regions are, the closer they appear to be in the emergent space. Take a breath and let this idea settle in your mind. The distance between your hand and this screen, the duration of time that has passed since you began listening, these might not be fundamental features of reality. They might be emergent properties of how quantum information is organized and correlated in a realm beyond space and time. This perspective radically reframes our understanding of what it means to exist. You and I, the Earth and the stars, all the matter and energy in the universe, we might all be patterns of information dancing in an abstract quantum realm. What we experience as three-dimensional space and flowing time might be the way these information patterns appear to subsystems, like ourselves, that are embedded within them. The implications extend far beyond theoretical physics. If space-time emerges from quantum entanglement, then the very concept of locality, the idea that things only directly influence their immediate neighbours, must be reconsidered. In the quantum information realm that underlies space-time, distant events might be intimately connected through patterns of entanglement that transcend our usual notions of spatial separation. As we venture further into these ideas, we encounter one of the most mind-bending concepts in modern physics, the holographic principle. This isn't science fiction, though it might sound like it. It's a rigorous mathematical framework that suggests our entire three-dimensional reality might be encoded on a two-dimensional surface. The principle emerged from the study of black hole thermodynamics. When physicists calculated the entropy of a black hole, they found something unexpected. The amount of information that could be stored in a black hole depends not on its three-dimensional volume, but on the area of its two-dimensional surface. This was surprising because we usually think of information storage capacity as proportional to volume, like the number of books you can fit in a library. But black holes seem to store information differently. Every bit of information that falls into a black hole appears to leave its mark on the event horizon, the two-dimensional boundary between the black hole's interior and the outside universe. The three-dimensional interior, no matter how vast, can hold no more information than what can be encoded on its two-dimensional surface. This discovery led to a remarkable generalization. Perhaps all of three-dimensional space, not just black holes, has this holographic property. Perhaps everything that happens in our three-dimensional universe, including your thoughts as you listen to this, is completely described by information encoded on a distant two-dimensional boundary. The mathematics of string theory has provided concrete realizations of this idea through what's called the ADS/CFT correspondence. This correspondence shows that certain theories of quantum gravity in curved spacetime are mathematically identical to quantum field theories without gravity living on the boundary of that spacetime. Everything that happens in the three-dimensional interior, including the formation of black holes, the collision of particles, and the evolution of spacetime itself, is perfectly mirrored by events in the two-dimensional boundary theory. As you listen to this, try to imagine what it might mean for your own existence. If the holographic principle applies to our universe, then you might be simultaneously a three-dimensional being living in space and time, and a pattern of information encoded on a distant two-dimensional surface. Both descriptions would be equally valid, equally real, just different ways of organizing the same fundamental information. This isn't merely a philosophical curiosity, The holographic principle has practical implications for how we understand quantum gravity, black hole physics, and the nature of information itself. It suggests that the universe might be far more economical with information than we previously imagined, encoding all of three-dimensional reality in two-dimensional terms. Here's something that might surprise you about the nature of reality. The stable, persistent space-time we experience might exist only because the universe is constantly performing quantum error correction, like a cosmic computer maintaining its data integrity against random noise and interference. This idea emerges from thinking about how the holographic principle might actually work in practice. If our three-dimensional reality is encoded in quantum information on a two-dimensional boundary, that information must be incredibly fragile. Quantum systems are notoriously susceptible to decoherence and noise. Without some mechanism to protect the information, the encoding of spacetime should rapidly degrade and space and time themselves should become unstable. Yet spacetime appears remarkably stable. The laws of physics remain constant across vast distances and timescales. The geometry of space doesn't randomly fluctuate in ways that would make life impossible. This stability might be evidence that the universe employs quantum error correction to maintain the integrity of space-time itself. In quantum error correction, information is encoded redundantly across many quantum systems, so that if some of the systems become corrupted, the original information can be recovered. The key insight is that the quantum entanglement between different parts of the system serves as the error-correcting mechanism. When parts of the system become entangled in specific patterns, they can detect and correct errors in other parts. Recent research suggests that the same mechanism might operate in quantum gravity. The entanglement patterns that give rise to emergent spacetime might simultaneously serve to protect that spacetime against quantum fluctuations. The geometric relationships we experience as space and time might be error-corrected codes, maintained by the quantum entanglement structure of the underlying information. Take a moment to appreciate the elegance of this idea. The same quantum entanglement that creates the illusion of space and time also preserves that illusion against the chaos of quantum uncertainty. We live in a reality that is simultaneously fragile because it's made of quantum information and robust because it's protected by quantum error correction. This perspective also offers new insights into what happens when quantum error correction fails. In regions where the entanglement structure becomes too damaged to maintain error correction, spacetime itself might break down. This could provide a new way to understand black hole interiors, cosmic singularities, and other extreme environments where classical spacetime physics fails. As we approach the deeper implications of quantum spacetime, we encounter a question that has puzzled physicists and philosophers for decades. What role does observation play in the quantum realm, and how does this role change when spacetime itself becomes quantum? In standard quantum mechanics, the act of measurement seems to play a special role in determining the outcome of quantum events. Before measurement, a quantum system exists in a superposition of all possible states. After measurement, it appears to collapse into a single, definite state. This measurement problem has generated countless interpretations and debates about the nature of quantum reality. But when spacetime itself becomes quantum, the measurement problem takes on new dimensions. If space and time emerge from quantum information, then the very notion of a measurement occurring at a definite place and time becomes problematic. How can we define the location and timing of a measurement when location and time are themselves quantum variables? Some interpretations suggest that consciousness might play a role in the emergence of classical spacetime from quantum information. This remains highly speculative, and no scientific consensus exists on such ideas. However, the mathematical frameworks of quantum gravity do suggest that the emergence of spacetime requires some form of coarse graining or information processing that selects certain quantum correlations while ignoring others. In this view, what we call classical spacetime might be the result of a particular way of organizing and processing quantum information. Different ways of organizing this information might give rise to different emergent spacetimes, or perhaps to realities that don't have spatial and temporal structure at all. This suggests a deep connection between information processing and the nature of reality itself. The patterns of correlation and entanglement that we identify as space and time might depend on how information flows and is processed within the underlying quantum system. From this perspective, space-time is not just the stage upon which physical processes occur. It is itself a form of information processing. As you contemplate this idea, notice how it blurs the traditional boundary between observer and observed. If space-time emerges from information processing, then any system that processes information, including conscious observers like ourselves, participates in the creation of the reality we experience. This doesn't mean that our thoughts directly influence quantum events or create physical reality through intention. That would be an overreach beyond what the science supports. But it does suggest that the very existence of information processing systems, like brains, might be intimately connected to the emergence of the space-time framework within which those brains exist. Of all the puzzles that emerge when space-time becomes quantum, perhaps none is more profound than the problem of time itself. In our everyday experience, time flows steadily forward, providing the backdrop against which all change and evolution occurs. We measure durations, sequence events, and organize our lives around the assumption that time is a fundamental aspect of reality. But in the quantum gravity realm, time loses this special status. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe as a whole, contains no time parameter at all. It describes the universe as existing in a kind of eternal, timeless state, with no preferred moment that could be called now. This creates what physicists call the problem of time. If the fundamental description of quantum gravity is timeless, how does the flowing time we experience emerge? Why do we remember the past but not the future? What creates the arrow of time that seems to point inexorably from earlier to later? One approach to this puzzle suggests that time emerges from the entanglement structure of quantum information in much the same way that space does. In this view, what we experience as temporal duration is really a measure of how quantum correlations spread and evolve within the underlying information network. Different observers, embedded in different parts of the quantum information structure, might experience different temporal flows. Time becomes not a universal backdrop, but a relative property that depends on the observer's position and motion within the information network. This idea finds mathematical support in the relational approach to quantum mechanics, where all properties of quantum systems are defined relative to other quantum systems. Another intriguing possibility is that time emerges from the process of quantum decoherence itself. As quantum systems become entangled with their environments, pure quantum states evolve into mixed classical states. This decoherence process might provide the physical basis for the arrow of time, explaining why we see certain types of change and evolution, but not others. Recent research has even suggested that the flow of time might be connected to the expansion of quantum entanglement throughout the universe. As the universe evolves, quantum correlations spread to encompass larger and larger regions. The rate of this entanglement growth might be what we perceive as the passage of time. Take a breath and consider what this might mean for your own experience of temporality. The moments flowing by as you listen to this, the memories forming in your mind, the anticipation of what comes next. All of these might be manifestations of quantum entanglement spreading through the information structure that underlies your existence. As we near the culmination of our exploration, it's worth considering the experimental frontiers that might soon provide answers to these deep questions about quantum spacetime. While the Planck scale remains far beyond the reach of direct observation, ingenious physicists are developing indirect ways to probe the quantum nature of space and time. One of the most promising approaches involves studying the cosmic microwave background radiation, the ancient light that fills the universe and carries information about conditions in the early cosmos. If space-time has a discrete structure, or if it emerged from quantum information in the way these theories suggest, there might be subtle signatures embedded in this ancient radiation. Advanced space-based telescopes and ground-based observatories are now sensitive enough to detect incredibly small fluctuations in the cosmic microwave background. These fluctuations might carry the fingerprints of quantum spacetime, encoded in patterns too subtle for previous generations of instruments to detect. Another experimental frontier involves the behavior of quantum systems in strong gravitational fields. As technology advances, we're becoming capable of creating quantum experiments in environments where gravitational effects become significant. These experiments might reveal how quantum mechanics and gravity interact at scales much larger than the Planck length. For instance, researchers are beginning to explore how quantum entanglement behaves in curved spacetime, how gravitational time dilation affects quantum clocks, and whether gravitational fields can create or destroy quantum correlations. These experiments won't directly probe the Planck scale, but they might reveal signatures of the deeper quantum gravitational effects that become dominant at those scales. Perhaps most intriguingly, some physicists have proposed using quantum computers themselves as probes of spacetime structure. If spacetime emerges from quantum information processing, then sufficiently complex quantum computers might be able to simulate the emergence of space and time from first principles. These simulations wouldn't just be models of quantum gravity, they might actually create small patches of emergent spacetime within the quantum computer itself. As you imagine these future experiments, consider how they represent humanity's deepest attempt to understand the nature of existence itself. We're not content to simply experience space and time. We want to understand what they are, where they come from, and whether they're truly fundamental or merely emergent properties of something deeper. As our journey through quantum spacetime draws toward a close, let's return to a more personal question. What does it mean for you, right here, right now, to exist in a universe where space and time might not be fundamental? If the ideas we've explored tonight are correct, then every moment of your existence is far more mysterious and beautiful than it might initially appear. The chair you're sitting in, the air you're breathing, the neurons firing in your brain as you process these words, all of these exist within a framework of space and time that might itself be an emergent property of quantum information. This doesn't diminish the reality of your experience. If anything, it enriches it. You are not just a collection of particles moving through space and evolving through time. You are a pattern of information processing that participates in the very creation of the space-time framework within which you exist. The boundaries of your body, which seem so definite and clear, might be more fluid than they appear. If space emerges from quantum entanglement, then the entanglement patterns that define you extend far beyond your physical boundaries. You are connected, through quantum correlations, to every other part of the universe. This perspective doesn't support claims that your thoughts directly influence physical reality or that consciousness creates the external world. The emergence of space-time from quantum information is a collective phenomenon involving vast numbers of quantum degrees of freedom, not something controlled by individual minds or intentions. But it does suggest that the boundaries between self and cosmos, between observer and observed, are more subtle than our everyday experience suggests. You exist not as an isolated entity moving through space and time, but as an integral part of the information processing network that gives rise to space and time themselves. As you drift through your daily life, carrying these ideas with you, notice how they might shift your perception of ordinary experiences. The distance between your hand and your face, the duration of a heartbeat, the separation between yourself and the horizon, all of these might be manifestations of deeper patterns of quantum correlation and entanglement. This is not mysticism, but mathematics, not wishful thinking, but rigorous physics. The universe revealed by quantum gravity is stranger and more wonderful than our ancestors could have imagined. Yet it's also the universe we've always lived in. We're simply beginning to see it more clearly. If you enjoyed drifting through those explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. As we reach the boundaries of current human knowledge, it's humbling to acknowledge how much remains unknown about the quantum nature of space-time. The theories we've explored tonight represent our best current understanding, but they are far from complete. String theory offers one compelling vision of quantum gravity, but it remains unverified by experiment and may ultimately prove to be incorrect or incomplete. Loop quantum gravity provides another approach, with its own successes and limitations. The holographic principle and the emergence of space-time from quantum information represent promising directions, but they too remain speculative. What seems certain is that our classical notions of space and time as fundamental aspects of reality will need to be revised. Whether they emerge from quantum information, discrete geometric units, higher dimensional strings, or something else entirely, space and time are revealing themselves to be far more subtle and mysterious than we once believed. This ongoing revolution in our understanding of space-time connects to the deepest questions about the nature of existence itself. What does it mean to be? What is the relationship between mind and matter? How do conscious observers like ourselves fit into the quantum universe? These questions don't have easy answers, but they point toward a universe that is far richer and more mysterious than the mechanical cosmos imagined by earlier centuries of science. We live in a reality where the very foundations of existence are dynamic, quantum, and information theoretic. As research continues, new experimental techniques will probe deeper into these mysteries. Advanced gravitational wave detectors will search for signatures of quantum spacetime. Quantum computers will simulate the emergence of geometry from information. Space-based telescopes will scan the cosmic microwave background for traces of the universe's quantum birth. Each new discovery will either support or challenge the theoretical frameworks we've explored tonight. Science is a process of constant refinement, where beautiful theories must ultimately face the judgment of experimental reality. The true nature of quantum spacetime will be revealed not through pure thought, but through the patient accumulation of observational evidence. Yet even as we await these experimental results, the theoretical frameworks of quantum gravity already offer us something valuable, a new way of thinking about our place in the cosmos. We are not separate from the universe, observing it from the outside. We are patterns within the universe, participating in the information processing that gives rise to space, time, and physical reality itself. As our exploration draws to a close, take a moment to appreciate the extraordinary journey we've shared. We began with the simple question of when space-time becomes quantum, and we've discovered that this question leads to some of the deepest mysteries about the nature of existence itself. We've seen how the smooth fabric of Einstein's space-time begins to dissolve at the Planck scale, giving way to quantum foam and uncertainty. We've explored how space and time might emerge from quantum information, quantum entanglement, and quantum error correction. We've contemplated the possibility that our three-dimensional reality is holographically encoded on a two-dimensional boundary, and that time itself might emerge from the spreading of quantum correlations. These ideas challenge our most basic assumptions about reality, yet they emerge from rigorous mathematical analysis of our most fundamental theories. They represent humanity's best current understanding of how the quantum realm connects to the geometric realm, how information relates to space-time, and how observers like ourselves fit into the cosmic picture. The answer to our original question turns out to be both simple and profound. Space-time becomes quantum at the point where our classical descriptions break down and quantum effects dominate. But this isn't just a technical transition between different theoretical frameworks. It's a window into the deepest nature of reality itself. Whether space-time emerges from quantum information, discrete geometric units, or some other quantum foundation, the implications are revolutionary. We live in a universe where the very stage upon which existence plays out is itself dynamic, quantum, and emergent. Space and time are not the rigid backdrop of reality, but active participants in the cosmic dance of existence. As you return to your daily life, carrying these ideas with you, remember that the ordinary experiences of moving through space and experiencing the flow of time connect you to some of the deepest mysteries in all of science. Every step you take, every moment you experience, participates in the quantum emergence of the space-time framework that makes existence possible. The universe revealed by quantum gravity is stranger than we imagined, yet it's also more beautiful. It's a cosmos where information and geometry dance together, where observers and observed are intimately connected, where the boundaries between self and universe dissolve into quantum correlations. And perhaps most remarkably, it's a universe where conscious beings like ourselves can contemplate these mysteries, can use mathematics and experiment to probe the deepest foundations of reality, can find meaning and wonder in the quantum dance of existence itself. As we drift deeper into the quantum foundations of reality, we encounter a puzzle that has haunted physicists for nearly a century, yet takes on entirely new dimensions when space-time itself becomes quantum. It's a paradox that touches the very heart of what it means to observe, to know, and to exist within a universe that might be fundamentally uncertain about its own nature. Consider this curious fact. Every measurement we make, every observation that pins down a quantum property seems to require the very space-time framework that quantum gravity tells us is emergent and uncertain. We measure the position of a particle at a specific location and time, but what if location and time are themselves quantum variables that don't have definite values until they're measured. This creates what physicists call the measurement problem in quantum gravity, and it's far more profound than the familiar measurement problem of standard quantum mechanics. We're not just asking how quantum superpositions collapse into definite outcomes. We're asking how the very stage upon which measurements occur emerges from quantum uncertainty. Picture yourself trying to take a photograph, but the camera, the film, and even the light itself are all quantum superpositions that exist in multiple states simultaneously. How could such a system ever produce a definite image? This is the situation we face when trying to understand measurement in a quantum space-time. Yet somehow, measurements do occur. You observe definite outcomes. You experience a world with apparently stable spatial relationships and a consistent flow of time. The mystery is how this classical experience emerges from a quantum foundation that should, by all rights, be utterly uncertain about its own geometric structure. Recent research suggests that the answer might lie in the process of quantum decoherence, but applied to space-time itself. Just as quantum systems become classical through interaction with their environment, space-time might become classical through interaction with the matter and energy it contains. The presence of observers like ourselves, with our complex information processing capabilities, might play a role in selecting which of the many possible quantum spacetimes becomes actualized as our experienced reality. This doesn't mean that consciousness creates reality in some mystical sense. The process appears to be far more subtle and collective than that. Rather, the very existence of complex information processing systems like brains might contribute to the emergence of a stable, classical space-time framework through purely physical mechanisms. Think about what this implies for a moment. The universe might be engaged in a constant process of self-measurement, with every interaction between particles, every exchange of information, contributing to the ongoing construction of the space-time framework within which those very interactions occur. We exist within a reality that is continuously creating itself through the act of its own observation. Let's venture now into one of the most counterintuitive aspects of quantum space-time, the nature of empty space itself. What we call vacuum, the apparent nothingness between particles, turns out to be anything but empty when viewed through the lens of quantum physics. In the smooth space-time of classical physics, a vacuum is simply the absence of everything. No matter, no energy, no activity of any kind. But quantum mechanics paints a radically different picture. Even in the emptiest regions of space, quantum fields are constantly fluctuating, creating and destroying virtual particles in time frames so brief they seem to mock our intuitive sense of causality. These quantum vacuum fluctuations become even more fascinating when we consider that space-time itself might be subject to similar uncertainty. At the Planck scale, the vacuum might be a seething foam of quantum geometry, where tiny regions of space-time spontaneously curve, twist, and even disconnect from the rest of reality before reconnecting in new configurations. Imagine, if you will, a calm lake surface viewed from a great distance. It appears smooth and featureless, but approach closely and you see that the surface is alive with tiny ripples, waves, and disturbances. The quantum vacuum might be similar. From our macroscopic perspective, space-time appears smooth and continuous, but at the Planck scale, it might be a churning sea of geometric possibilities. These vacuum fluctuations of space-time aren't just theoretical curiosities. They might have observable consequences in our everyday world. Some calculations suggest that these quantum geometric fluctuations could contribute to the mysterious dark energy that appears to be accelerating the expansion of our universe. The energy of the quantum vacuum, rather than being a passive background, might be actively shaping the evolution of cosmic structure. As you contemplate this idea, notice how it transforms your understanding of the space around you. The seemingly empty air between your hands isn't truly empty. It's filled with quantum fields fluctuating at frequencies too rapid for your senses to detect. And even the geometric structure of that space, the very framework that allows the concept of between to have meaning, might be continuously fluctuating and reforming at scales too small for any instrument to measure. This dancing quantum vacuum connects to some of the deepest questions about the nature of existence. If space-time itself is subject to quantum uncertainty, if the very foundation of reality is continuously fluctuating between different possible configurations, what does this say about the nature of permanence, stability, and identity? Perhaps the remarkable thing isn't that quantum space-time is uncertain and fluctuating. Perhaps the remarkable thing is that stable, coherent structures like stars, planets, and conscious beings can emerge from this quantum foundation at all. We are islands of relative stability in a sea of quantum uncertainty, patterns of information that maintain their coherence despite existing within a fluctuating space-time foam. As we continue our exploration of quantum space-time, we encounter a puzzle that reveals deep connections between the structure of space, the flow of time, and the nature of memory itself. This puzzle emerges from thinking carefully about what happens to information when space-time becomes quantum. In classical physics, information has a straightforward relationship to space-time. Events occur at definite locations and times, and the information about those events can, in principle, be preserved indefinitely. The past exists as a collection of facts about what happened, where, and when. Memory, whether stored in brains, books, or computer hard drives, is simply a way of encoding and preserving these facts about past events. But in quantum space-time, this simple picture breaks down. If space and time are themselves quantum variables, then the very notion of an event occurring at a definite location and time becomes problematic. How can information be stored about the where and when of an event if where and when are quantum superpositions that don't have definite values? This creates what we might call the quantum memory paradox. How can any system, whether a human brain or a cosmic database of information, store memories of past events if the space-time framework within which those events occurred is itself uncertain and fluctuating? One possible resolution suggests that memory might not be a passive storage of information about past events, but an active process that participates in the creation of the past itself. When you remember something, you're not simply accessing stored data about a fixed historical fact. You might be participating in the ongoing quantum measurement process that gives definite meaning to past events. Consider how this might transform your understanding of your own memories, the childhood experiences you recall, the conversations you had yesterday, the moment you began listening to this exploration. These might not be fixed facts about a predetermined past. They might be continuously constructed through the ongoing interaction between your memory-forming processes and the quantum space-time structure that connects past and present. This doesn't mean that memories are unreliable or that the past is entirely subjective. Rather, it suggests that the relationship between present memory and past events is far more subtle and participatory than we usually imagine. The act of remembering might be a form of quantum measurement that helps to crystallize the uncertain quantum history into definite classical facts. As you listen to these ideas, pause for a moment and consider your own experience of memory. Notice how memories aren't simply retrieved like files from a computer, but are actively reconstructed each time you remember them. Recent neuroscience research confirms that each act of remembering actually changes the memory being recalled. What if this reconstructive nature of memory reflects something deeper about the quantum structure of time itself? This perspective also offers new insights into the nature of identity and continuity. If your memories participate in the ongoing construction of your personal past, then you are not simply a product of your history. You are an active participant in creating that history through the ongoing process of remembering and forgetting, of attending and ignoring, of weaving the quantum possibilities of the past into the definite narrative of your experienced life. As our journey through quantum spacetime deepens, we arrive at perhaps the most profound and speculative territory of all: the possible connections between the quantum nature of spacetime and the emergence of consciousness itself. This remains one of the most contentious and uncertain areas in both physics and neuroscience, yet the questions it raises are too important to ignore completely. Let's proceed carefully here, acknowledging from the outset that we're venturing into territory where scientific understanding remains incomplete and where speculation often exceeds what the evidence can support. No scientific consensus exists on whether quantum mechanics plays any special role in consciousness, and many neuroscientists believe that classical physics is sufficient to explain all aspects of brain function. However, the mathematical frameworks of quantum gravity do raise intriguing questions about the nature of information processing in a universe where space-time itself emerges from quantum correlations. If consciousness involves the integration of information across different regions of the brain, and if space itself emerges from quantum entanglement, then it's natural to wonder whether these phenomena might be connected in some way. Consider the binding problem in consciousness research. How does the brain integrate information from different sensory modalities and different regions of neural activity into a unified, coherent experience? You simultaneously see colours, hear sounds, feel sensations, and think thoughts. Yet these different streams of information somehow combine into a single, integrated conscious experience. Some speculative theories suggest that quantum entanglement might provide a mechanism for this integration, allowing different regions of the brain to share information in ways that transcend classical notions of spatial separation. If the brain operates as a quantum information processor, then consciousness might emerge from the same types of quantum correlations that give rise to spacetime itself. This is a highly speculative idea, and it's important to emphasize that no experimental evidence currently supports it. The brain appears to be a warm, noisy, classical environment where quantum effects would typically be destroyed by decoherence long before they could influence neural computation. Most neuroscientists believe that consciousness emerges from classical neural networks without requiring any special quantum effects. Yet the mathematical parallels between quantum information processing and certain features of consciousness continue to intrigue researchers. Both involve the integration of information across distributed systems, both exhibit non-local correlations, and both seem to involve the emergence of higher-level properties from lower-level quantum or neural processes. As you consider these ideas, remember that consciousness remains one of the deepest mysteries in all of science. We don't yet understand how subjective experience arises from objective physical processes, whether those processes are classical or quantum. The hard problem of consciousness, the question of why there is something it's like to be conscious, remains unsolved regardless of which physical framework we employ. What quantum spacetime does offer is a new context for thinking about these old questions. If spacetime itself emerges from information processing, if observers play a role in the actualization of quantum possibilities, if the boundary between self and cosmos is more fluid than classical physics suggests, then perhaps consciousness isn't something separate from the physical universe, but rather an integral part of the information processing network that gives rise to physical reality itself. This remains deeply speculative, and it's crucial not to overstate what current science can support. But it's also important to remain open to the possibility that our understanding of consciousness, like our understanding of space-time, might need to be fundamentally revised as we learn more about the quantum nature of reality. Let's step back now from these speculative territories and consider something more concrete yet equally profound: how quantum spacetime might manifest on the largest scales of cosmic structure. The universe as we observe it today is organized into a vast web of galaxies, galaxy clusters, and cosmic voids, connected by filaments of dark matter and ordinary matter that span hundreds of millions of light years. This cosmic web represents one of the most striking features of our universe, yet its origins remain mysterious. How did the smooth, nearly uniform conditions of the early universe evolve into the complex hierarchical structure we see today? Standard cosmology provides a framework for understanding this evolution, but quantum spacetime theories suggest that the story might be far richer and more subtle than we currently realize. If spacetime itself has quantum origins, then the seeds of cosmic structure might be quantum mechanical in nature. The tiny fluctuations in the cosmic microwave background radiation, which are thought to be the precursors of galaxies and galaxy clusters, might be direct traces of quantum spacetime effects from the earliest moments of cosmic history. Some theories suggest that these fluctuations might carry signatures of the discrete or holographic nature of spacetime itself. If space has a granular structure at the Planck scale, or if our three-dimensional reality is holographically encoded on a two-dimensional boundary, there might be subtle patterns in the cosmic microwave background that reveal these deep structural features of spacetime. Imagine the cosmic web not just as a pattern of matter distribution, but as a manifestation of the quantum correlation structure that underlies spacetime itself. The filaments that connect distant galaxies might trace the patterns of quantum entanglement that give rise to spatial relationships on cosmic scales. This perspective suggests that when we look up at the night sky and observe the large-scale structure of the universe, we might be seeing a direct reflection of the quantum information architecture that underlies all of reality. The cosmic web becomes not just an arrangement of matter and energy, but a visible representation of the entanglement patterns that weave space and time together. As you contemplate this idea, consider how it connects the most intimate aspects of quantum mechanics to the grandest scales of cosmic structure. The same principles that govern the behavior of individual particles in laboratory experiments might also shape the distribution of galaxies across billions of light years. The quantum and the cosmic might be intimately connected through the underlying information structure of spacetime itself. This connection between quantum mechanics and cosmology has practical implications for how we search for evidence of quantum spacetime effects. Rather than waiting for technology that can probe the Planck scale directly, we might be able to detect signatures of quantum spacetime by studying the statistical properties of cosmic structure on the largest observable scales. Current and future astronomical surveys are mapping the cosmic web with unprecedented precision, measuring the positions and properties of millions of galaxies across vast regions of space. Hidden within these vast datasets might be the subtle signatures of quantum spacetime, waiting to be discovered by sufficiently clever analysis techniques. As we venture toward the outer boundaries of current theoretical understanding, we encounter one of the most mind-expanding possibilities suggested by quantum spacetime theories: the existence of multiple, distinct spacetimes emerging from the same underlying quantum information substrate. This isn't the familiar multiverse of branching quantum possibilities, where every quantum measurement creates parallel universes with different outcomes. This is something far more fundamental: the possibility that different patterns of quantum correlation and entanglement might give rise to entirely different spacetime geometries, with different numbers of dimensions, different causal structures, and different physical laws. In this view, our familiar three-dimensional space plus time might be just one possible way that quantum information can organize itself into a geometric structure. Other patterns of quantum correlation might give rise to spaces with more or fewer dimensions, or to geometries that don't conform to our usual notions of space and time at all. Some versions of string theory suggest that this is not merely possible, but inevitable. In the landscape of string theory, there might be an enormous number of different ways that quantum information can organize itself into stable space-time geometries. Our universe, with its particular laws of physics and geometric structure, would be just one island in a vast ocean of possible realities. Take a breath and consider what this might mean for the nature of existence itself. The space-time framework that contains your entire life history, every thought you've ever had, every relationship you've formed, might be just one of countless possible geometric arrangements of quantum information. Somewhere in the quantum substrate that underlies all possible realities, other spacetimes might exist with their own physics, their own forms of structure and complexity, their own possibilities for the emergence of conscious observers. This perspective radically expands our notion of what it means for something to be real. Reality becomes not a single, definite structure, but a vast landscape of possibilities, most of which remain forever inaccessible to observers like ourselves, who are embedded within a particular space-time geometry. Yet this multiplication of realities doesn't diminish the significance of our own existence. If anything, it makes our particular corner of the quantum multiverse more precious and remarkable. The fact that quantum information has organized itself in just the right way to give rise to a space-time that can support the emergence of stars, planets, life, and consciousness becomes an extraordinary stroke of cosmic fortune. This perspective also offers new insights into the apparent fine-tuning of physical constants that make life possible in our universe. Rather than needing to explain why our particular universe has just the right properties for complexity and consciousness to emerge, we might simply be observing the fact that we necessarily find ourselves in a space-time that permits our existence. Other space-times, with different physical laws, might exist in the quantum multiverse, but they wouldn't contain observers capable of contemplating their own existence. As you let these ideas settle in your mind, notice how they transform the question of why we exist from a cosmic puzzle into a logical necessity. In a quantum multiverse of emergent spacetimes, conscious observers like ourselves must necessarily find themselves in spacetimes compatible with consciousness, just as aquatic creatures necessarily find themselves in environments containing water. As we approach the deepest levels of our exploration, we encounter the emerging recognition that quantum gravity and quantum information theory are not separate fields of physics, but different perspectives on the same underlying reality. This convergence represents one of the most exciting developments in modern theoretical physics, promising to revolutionize our understanding of space, time, matter, and information. The connection begins with a simple but profound observation. Information appears to be indestructible. In quantum mechanics, the total amount of information in any closed system remains constant over time, even as that information might be scrambled, encoded, or transformed in complex ways. This principle of information conservation has been tested extensively in laboratory experiments and appears to be one of the most fundamental laws of nature. But when we apply this principle to black holes, we encounter the information paradox we discussed earlier. Black holes appear to destroy information when they evaporate through Hawking radiation, violating the principle of information conservation. The resolution of this paradox has led physicists to recognize that information and geometry are far more intimately connected than previously imagined. Recent advances in quantum information theory have shown that the geometric relationships we interpret as space and time can emerge naturally from the entanglement structure of quantum information. When quantum systems become entangled in particular patterns, they spontaneously give rise to geometric relationships that behave exactly like the curved space-time of Einstein's general relativity. This emergence of geometry from entanglement isn't just a mathematical curiosity. It appears to be a fundamental feature of how reality organizes itself. The spatial relationships between different parts of your body, the temporal duration of your thoughts, the causal connections between events in your life, all of these might be manifestations of quantum entanglement patterns in an underlying information processing substrate. Consider how this transforms our understanding of what it means to be spatially separated from something else. In classical physics, distance is simply a measure of how much space lies between two objects. But if space emerges from quantum entanglement, then distance becomes a measure of how strongly two systems are quantum mechanically correlated with each other. This suggests that the feeling of separation between yourself and the world around you might be, in some sense, an illusion created by the particular pattern of quantum correlations that gives rise to your local space-time environment. At a deeper level, you might be far more intimately connected to the rest of the universe than your everyday experience suggests. The mathematics of this connection between information and geometry has led to remarkable insights about the nature of quantum error correction in the universe itself. If space-time emerges from quantum information, then the stability of space and time might depend on error correction mechanisms that protect the underlying information from decoherence and noise. Some researchers have proposed that the universe might be a vast quantum computer, constantly processing information and performing error correction to maintain the stability of space-time itself. From this perspective, every physical interaction, every exchange of energy and momentum contributes to the ongoing computation that sustains the reality we experience. As you contemplate this idea, notice how it reframes your relationship to the physical world around you. Every breath you take, every step you make, every thought that crosses your mind participates in the vast quantum computation that maintains the space-time framework within which your existence unfolds. You are not separate from this computation. You are part of it. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. As we delve deeper into the implications of quantum spacetime, we encounter one of the most fundamental questions in all of physics. What creates the causal structure of reality? Why do causes precede effects? Why can we influence the future, but not the past? Why does information appear to flow in a preferred direction through time? In classical physics, causality seems straightforward. Events occur at definite locations and times, and the causal relationships between them are determined by the speed of light and the geometry of spacetime. The future is influenced by the past through the propagation of physical effects across space at finite speeds. But in quantum spacetime, this simple picture becomes remarkably complex. If space and time themselves emerge from quantum information processing, then the causal structure of reality must also emerge from the patterns of quantum correlation and entanglement that give rise to spacetime geometry. Recent research in quantum gravity has revealed that causality itself might be a quantum phenomenon. The causal relationships between events might not be fixed and definite, but might exist in quantum superpositions, just like other quantum properties. In certain extreme situations, such as in the vicinity of quantum black holes, or during the earliest moments of cosmic inflation, the very notion of which events cause which other events might become fundamentally uncertain. This quantum nature of causality has profound implications for our understanding of time and temporal experience. The arrow of time that we experience in our daily lives, the sense that the future is open, while the past is fixed, might emerge from the way quantum information flows and processes itself within the spacetime structure that contains our existence. Some theories suggest that consciousness itself might play a role in establishing causal relationships through the process of quantum measurement. When conscious observers make measurements, they might not just be revealing pre-existing causal relationships, but actually participating in the creation of those relationships through the act of observation itself. This doesn't mean that consciousness controls causality in any direct or intentional way. Rather, it suggests that the emergence of classical causal structure from quantum foundations might require the presence of information processing systems capable of making measurements and storing memories. The universe might need observers in order to have a definite causal structure. As you consider these ideas, think about your own experience of causality and temporal flow. The sense that your actions today will influence tomorrow, that your memories connect you to yesterday, that decisions lead to consequences. All of these familiar aspects of temporal experience might be manifestations of deeper quantum processes that establish causal relationships within the emergent spacetime framework of reality. This perspective offers new insights into the nature of free will and determinism. If causality itself emerges from quantum processes, then the future might be genuinely open in ways that classical physics never allowed. The choices you make, the paths you take, the intentions you form might participate in the ongoing creation of causal relationships rather than simply following predetermined causal chains. As our exploration of quantum spacetime draws toward its culmination, let's step back and appreciate the extraordinary symphony of ideas we've encountered. From the breakdown of classical spacetime at the Planck scale, to the emergence of geometry from quantum information, from the holographic encoding of three-dimensional reality on two-dimensional boundaries, to the possible quantum origins of consciousness itself, we've traced a path through some of the deepest mysteries about the nature of existence. What emerges from this exploration is a vision of reality that is far more subtle, interconnected, and participatory than the mechanical universe imagined by earlier centuries of science. We don't live in a world of separate objects moving through fixed space and time according to predetermined laws. Instead, we inhabit a universe where space and time themselves are dynamic, emergent properties of a deeper quantum information substrate. In this quantum universe, the boundaries between observer and observed, between self and cosmos, between information and geometry become fluid and permeable. You are not an isolated entity moving through space and time. You are a pattern of information processing that participates in the very creation of the space-time framework within which your existence unfolds. The matter that composes your body, the thoughts that flow through your mind, the relationships that connect you to other conscious beings, all of these exist within and contribute to the vast quantum computation that maintains the stability and coherence of reality itself. Every moment of your existence participates in the ongoing emergence of space and time from quantum foundations. This perspective doesn't diminish the reality or significance of your everyday experience. The love you feel for others, the beauty you perceive in art or nature, the meaning you find in your work and relationships, all of these remain as real and important as ever. But they exist within a context that is far richer and more mysterious than classical physics suggested. The quantum nature of space-time also offers new perspectives on some of the deepest questions about existence. Why is there something rather than nothing? Perhaps because quantum information naturally organizes itself into patterns that we recognize as space, time, matter, and energy. Why does the universe appear fine-tuned for the existence of complexity and consciousness? Perhaps because we necessarily find ourselves in a quantum space-time that permits our existence. Why do we experience a sense of individual identity despite being composed of particles that are constantly exchanging with the environment? Perhaps because identity emerges from stable patterns of information processing within the quantum correlation networks that give rise to space-time itself. As you listen to these ideas, take a moment to appreciate how they connect to your direct experience. The sense of being located in space, of moving through time, of being separate from yet connected to the world around you. All of these familiar aspects of consciousness might be windows into the quantum nature of reality itself. As we look toward the future of quantum space-time research, we stand at the threshold of what might be the most exciting period in the history of physics. For the first time, we have both the theoretical frameworks and the experimental capabilities to begin probing the deepest questions about the quantum nature of reality using instruments we're only now learning to build. The next generation of gravitational wave detectors, such as the proposed Einstein telescope and Cosmic Explorer, will be sensitive enough to detect space-time distortions that are orders of magnitude smaller than current instruments can measure. These detectors might reveal signatures of quantum space-time that have been hidden until now, subtle deviations from classical general relativity that could confirm or refute our most ambitious theories about the quantum nature of geometry. Space-based gravitational wave observatories, like the planned LISA mission, will open entirely new windows into quantum space-time phenomena, operating in the pristine environment of space, free from terrestrial vibrations and noise. These instruments will be able to detect gravitational waves across a much broader frequency range than ground-based detectors. They might reveal quantum effects in space-time that manifest only over cosmic distances and astronomical timescales. Perhaps most intriguingly, advances in quantum technology itself are creating new opportunities to probe the intersection between quantum mechanics and gravity. Quantum sensors based on trapped atoms, superconducting circuits, and other quantum systems are becoming sensitive enough to detect gravitational effects on quantum states. These experiments won't directly probe the Planck scale, but they might reveal how gravity influences quantum coherence and entanglement in ways that could illuminate the deeper quantum structure of space-time. Some researchers have proposed using quantum computers as simulators of quantum space-time itself. If space-time truly emerges from quantum information processing, then sufficiently powerful quantum computers might be able to create small patches of emergent space-time within their quantum memory. These simulations wouldn't just model quantum gravity, they might actually instantiate it, creating genuine examples of emergent space-time that we could study and manipulate in controlled laboratory conditions. Take a moment to imagine what it might mean to create space-time in a laboratory. The idea sounds like science fiction, yet it emerges naturally from the theoretical frameworks we've explored tonight. If space and time are truly emergent properties of quantum information processing, then creating artificial space-time becomes a matter of engineering the right patterns of quantum correlation and entanglement. As we approach the conclusion of our journey through quantum space-time, it's worth pausing to consider the profound philosophical implications of the ideas we've encountered. These aren't merely technical questions about the mathematical structure of physical theories. They touch the deepest questions about the nature of existence, identity, consciousness, and meaning itself. If space-time emerges from quantum information, what does this say about the nature of physical reality? The traditional view of physics assumes that there is an objective, observer-independent reality that exists whether or not anyone is there to observe it. But quantum space-time theories suggest that reality might be far more participatory and observer-dependent than this classical view allows. This doesn't mean that reality is subjective, or that individual minds create the external world through their beliefs or intentions. The emergence of space-time from quantum information appears to be a collective phenomenon involving vast numbers of quantum degrees of freedom, not something controlled by individual consciousness or personal will, but it does suggest that the sharp distinction between observer and observed, between mind and world, between subject and object, might be less fundamental than we typically assume. If observers like ourselves are patterns of information, processing embedded within the same quantum substrate that gives rise to space-time, then we are not separate from the reality we observe. We are part of it, participating in its ongoing creation through the very act of our existence. This perspective offers new ways of thinking about some of the oldest philosophical questions. What is the relationship between mind and matter? Perhaps they're both patterns of information, processing within the quantum substrate that underlies all reality. What is the nature of personal identity over time? Perhaps identity emerges from stable patterns of quantum correlation that persist even as the underlying information is constantly processing and transforming. What does it mean to be conscious in a quantum universe? Perhaps consciousness is not something separate from the physical world, but rather a particular type of information processing that participates in the same quantum correlation networks that give rise to spacetime itself. These ideas remain highly speculative, and it's crucial to emphasize that no scientific consensus exists on the relationship between consciousness and quantum mechanics. Most neuroscientists and physicists believe that consciousness can be understood through classical physics without invoking special quantum effects. The ideas we're exploring here represent just one possible direction for future research, not established scientific fact. Yet the questions themselves are important, regardless of how they're ultimately answered. The quantum revolution in physics has already transformed our understanding of matter, energy, space, and time. As we begin to grapple with the quantum nature of space-time itself, we might need to similarly revise our understanding of consciousness, identity, and meaning. As you consider these possibilities, notice how they might shift your perspective on your own existence. You're not just a collection of particles that happen to organize themselves into a thinking being. You are a pattern of information processing that participates in the ongoing creation of the space-time framework within which all existence unfolds. There's something deeply poetic about the vision of reality that emerges from quantum space-time theories. We inhabit a universe where the most fundamental levels of existence dance between certainty and possibility, where space and time themselves emerge like music from the quantum symphony of information processing. Consider the elegant paradox at the heart of quantum space-time. The very framework that makes measurement and observation possible emerges from processes that transcend measurement and observation. Space and time, the stage upon which all physical events unfold, arise from a quantum realm that exists before and beyond spatial and temporal relationships. This creates what we might call the quantum poetry of existence. We are patterns of information that have become complex enough to contemplate their own informational nature. We are space-time structures that have evolved the ability to question the nature of space-time itself. We are quantum processes that have achieved the capacity to probe their own quantum foundations. There's something both humbling and empowering about this perspective. Humbling because it reveals how much we still don't understand about the most basic features of reality. Empowering because it suggests that we are not passive observers of a predetermined universe, but active participants in its ongoing creation. The breath you're taking right now, the thoughts flowing through your consciousness as you listen, the quantum correlations that maintain the stability of the atoms in your body, all of these participate in the vast information processing network that sustains the reality we share. You are not separate from the universe. You are a way that the universe has learned to experience and understand itself. This participatory view of existence doesn't diminish the significance of individual experience or choice. If anything, it suggests that every moment of conscious awareness, every decision you make, every relationship you form, contributes to the ongoing evolution of the cosmic information processing network that gives rise to space-time itself. As you listen to these words, you're engaging in a form of information processing that connects your individual consciousness to the broader patterns of quantum correlation that underlie all of reality. The meaning you find in these ideas, the questions they raise in your mind, the sense of wonder or confusion they might evoke, all of these are expressions of the same fundamental information processing that creates space, time, and physical existence itself. As we near the end of our exploration, it's important to acknowledge that every answer we've discovered tonight raises new and deeper questions. This is the nature of scientific inquiry at its most fundamental level. Each layer of understanding we peel back reveals new mysteries hiding beneath. If spacetime emerges from quantum information, what gives rise to the quantum information itself? If consciousness participates in the creation of reality through observation and measurement, what creates consciousness? If the universe is engaged in vast information processing computations that maintain the stability of spacetime, what is the purpose or direction of this cosmic computation? These questions don't have easy answers, and some of them might not have answers at all within our current frameworks of understanding. They point toward horizons of knowledge that remain beyond our reach, mysteries that future generations of scientists and philosophers will need to grapple with. Yet the very existence of these questions is itself remarkable. In a universe where spacetime emerges from quantum information, the fact that information processing systems, like human minds, can formulate questions about their own foundations represents an extraordinary development in the cosmic evolution of complexity. We are not just products of the universe. We are ways that the universe has learned to ask questions about itself. The scientific theories we develop, the experiments we design, the philosophical frameworks we construct, all of these are expressions of the universe's ongoing attempt to understand its own nature. This perspective transforms the entire enterprise of science from a human activity imposed upon a passive natural world into a cosmic process of self-discovery. When we probe the quantum foundations of spacetime, we are not external observers studying an alien reality. We are the universe investigating itself through the information processing capabilities it has evolved within conscious beings like ourselves. As you think about returning to your daily life after this exploration, consider carrying this sense of cosmic participation with you. The seemingly ordinary activities of thinking, observing, remembering, and choosing all connect you to the deepest levels of reality. Every moment of conscious awareness is an expression of the quantum information processing that creates and maintains the universe itself. One of the most beautiful aspects of quantum spacetime research is how it preserves and even enhances the sense of mystery and wonder that draws us to contemplate existence in the first place. Rather than reducing reality to a collection of mechanical processes, quantum gravity reveals a universe that is far more subtle, participatory, and open to possibility than classical physics ever imagined. The mathematical frameworks we've explored tonight, from the Wheeler-DeWitt equation to the holographic principle, from loop quantum gravity to emergent spacetime theories, all point toward a reality that transcends our everyday categories of understanding. We find ourselves in a universe where the most fundamental questions about space, time, matter, and consciousness remain beautifully open. This openness isn't a failure of scientific understanding. It's a reminder that reality is far richer and more mysterious than any finite framework of knowledge can fully encompass. The quantum nature of space-time ensures that there will always be deeper levels of mystery to explore, new questions to ask, new horizons of understanding to pursue. As you contemplate your place in this quantum universe, remember that you are part of an ongoing cosmic story that is still being written. The choices you make, the relationships you form, the consciousness you bring to each moment, all of these contribute to the unfolding narrative of reality itself. The universe is not a finished product that we observe from the outside. It is a dynamic, evolving process that we participate in through the very act of existing. Your thoughts, your experiences, your questions about the nature of existence, all of these are threads in the vast tapestry of quantum information that weaves space and time together. There's something profoundly hopeful about this vision of reality. If the universe is indeed engaged in an ongoing process of self-discovery through the consciousness it evolves, then every moment of awareness, every act of questioning, every attempt to understand contributes to the cosmic project of existence, understanding itself. Take a deep breath and let yourself feel connected to this vast process. You are not an isolated fragment of consciousness accidentally thrown into an indifferent universe. You are an expression of the universe's deepest capacity for self-awareness and understanding. Through your consciousness, the quantum foundations of reality become capable of contemplating themselves. As our journey through quantum space-time approaches its conclusion, we find ourselves standing before a kind of cosmic mirror. In seeking to understand the quantum foundations of space and time, we have discovered profound reflections of the mystery of our own existence. The participatory nature of quantum measurement mirrors the participatory nature of consciousness itself. Just as quantum systems seem to exist in superposition until they are observed, our own experiences often exist in states of uncertainty and possibility until we bring focused attention to them. The entanglement that gives rise to spatial relationships in quantum gravity theories echoes the deep interconnectedness we sense in our relationships with others and with the natural world. The holographic principle, which suggests that all information in a volume can be encoded on its boundary, resonates with the intuition that consciousness somehow contains or reflects the entire universe within itself. These parallels don't prove that consciousness operates through quantum mechanisms. The brain appears to be largely a classical system, and most neuroscientists believe that quantum effects are not necessary to explain cognitive function. But the mathematical structures that describe quantum spacetime do offer new metaphorical frameworks for thinking about the nature of consciousness and its relationship to physical reality. Perhaps consciousness and quantum spacetime are both expressions of something even more fundamental: the universe's capacity to process information, to create patterns of correlation and meaning, to bootstrap itself into ever more complex forms of organization and self-awareness. In this view, the emergence of consciousness from neural networks and the emergence of space-time from quantum information might be manifestations of the same underlying principle: the tendency of information to organize itself into coherent, self-sustaining patterns that transcend their individual components. As you reflect on your own conscious experience, notice how it exhibits many of the same features we've attributed to quantum space-time. Your consciousness is not localized to any single neuron or brain region, but emerges from patterns of correlation across distributed networks. Your sense of identity persists over time, despite the constant flux of thoughts, sensations, and memories. Your awareness seems to have a kind of non-local quality, capable of attending to multiple aspects of experience simultaneously. These similarities might be more than mere coincidence. They might reflect deep structural principles that govern how complex systems emerge from simpler components, whether those components are quantum bits of information or neural networks in the brain. As we prepare to conclude our exploration of quantum spacetime, let's return to the sense of wonder that brought us here in the first place. Throughout this long journey, we've encountered ideas that challenge our most basic assumptions about the nature of existence. We've seen how space and time, the most familiar aspects of our experienced reality, might emerge from abstract patterns of quantum information. We've contemplated the possibility that consciousness and space-time are intimately connected through the information processing that gives rise to both. We've explored how the boundaries between observer and observed, between self and cosmos become fluid and permeable when viewed through the lens of quantum gravity. These ideas remain at the frontier of human understanding. Many of them are highly speculative, supported more by mathematical elegance than by experimental confirmation. The true nature of quantum spacetime might turn out to be quite different from any of the theories we've discussed tonight. But regardless of which specific ideas prove correct, the deeper message remains profound. Reality is far stranger, more subtle, and more participatory than our everyday experience suggests. We live in a universe that is still revealing its secrets, still evolving new forms of complexity and consciousness, still engaged in the cosmic project of understanding itself. Your presence here tonight, listening to these ideas, contemplating these mysteries, participating in this exploration, is itself a remarkable expression of the universe's capacity for self-reflection. Through your consciousness, patterns of quantum information that emerged billions of years ago in the early universe have evolved the ability to contemplate their own foundations. But here, this is perhaps the most beautiful paradox of all. In seeking to understand the quantum origins of space-time, we discover that we ourselves are expressions of the very processes we're trying to understand. The observer and the observed, the questioner and the mystery, are aspects of a single, unfolding cosmic process of self-discovery. As you return to your daily life, carrying these ideas with you, remember that every moment of conscious awareness is a miracle of cosmic evolution. The thoughts you think, the relationships you form, the meaning you create, all of these emerge from the same quantum foundations that give rise to space, time, and physical reality itself. The universe is not a collection of separate objects moving through empty space according to predetermined laws. It is a vast, interconnected process of information processing and pattern formation, constantly creating new possibilities for complexity, consciousness, and understanding. You are not separate from this process. You are an expression of it, a way that the cosmos has learned to experience and contemplate its own nature. Through your existence, the quantum foundations of reality become capable of wondering about themselves. As our exploration draws to a close, we return to the question that began our journey. At what point does space-time become quantum? We've discovered that this seemingly simple question opens onto some of the deepest mysteries about the nature of existence itself. The answer, as we've seen, is both precise and profound. Space-time becomes quantum at the Planck scale, where the uncertainty principle of quantum mechanics begins to affect the geometry of space and time themselves. But this technical answer only scratches the surface of what it means for space-time to be quantum. The deeper answer is that space-time is always quantum, even at the scales we experience in daily life. The smooth, continuous space and time of our everyday experience emerge from quantum foundations, like waves arising from an ocean of possibility. We don't live on top of quantum space-time. We live within it, as expressions of the very quantum processes that create the geometric framework of reality. This perspective transforms our understanding of what it means to exist. We are not separate beings moving through a fixed background of space and time. We are patterns of information, processing that participate in the ongoing creation of the space-time framework within which all existence unfolds. The implications extend far beyond physics and philosophy. They touch the deepest questions about meaning, purpose, and possibility in a quantum universe. If reality is fundamentally participatory, if consciousness and cosmos are intimately connected through information processing, if the very foundations of existence remain open to possibility and change, then our choices, our awareness, our capacity for wonder and understanding all matter in ways we are only beginning to comprehend. The quantum nature of space-time doesn't give us magical powers to control reality through thought or intention, but it does suggest that we are far more intimately connected to the cosmic process than classical physics ever imagined. Through our consciousness, the universe achieves a form of self-awareness. Through our questions, it explores its own mysteries. Through our wonder, it experiences the beauty of its own existence. As you drift off to sleep tonight, perhaps you'll dream of quantum foam and emergent geometries, of holographic boundaries and entangled possibilities. These dreams, too, are expressions of the quantum information processing that creates and maintains reality. Even in sleep, you remain connected to the cosmic dance of existence. The question of when space-time becomes quantum has led us to the recognition that everything is always already quantum, including ourselves. We are quantum beings living in a quantum universe, participating in the ongoing quantum creation of space, time, and meaning itself. And in that participation, in that cosmic dance of consciousness and cosmos, we find not answers, but better questions. Not certainty, but deeper wonder. Not separation, but connection to the infinite mystery of existence itself. As we drift deeper into the quantum foundations of reality, we encounter a paradox so fundamental that it threatens to unravel our entire understanding of what it means to observe, to know, and to exist within a universe that might be perpetually uncertain about its own nature. Picture this curious situation. Every measurement we make, every observation that pins down a quantum property seems to require the very space-time framework that quantum gravity tells us is itself uncertain and emergent. We measure the position of a particle at what we call a specific location and time, but what if location and time are themselves quantum variables existing in superposition until they're measured? This creates what physicists call the measurement problem in quantum gravity, and it represents a challenge far more profound than the familiar measurement puzzles of standard quantum mechanics. We're not simply asking how quantum superpositions collapse into definite outcomes. We're questioning how the very stage upon which measurements occur emerges from quantum uncertainty in the first place. Take a breath and consider the strangeness of this situation. Imagine trying to take a photograph where the camera, the subject, and even the light itself exist in quantum superpositions. How could such a system ever produce a definite image? This is precisely the puzzle we face when trying to understand observation in a quantum space-time. Yet somehow, measurements do occur. You observe definite outcomes right now as you listen. You experience a world with apparently stable spatial relationships and a consistent flow of time. The mystery lies in understanding how this classical experience emerges from quantum foundations that should, by all rights, be utterly uncertain about their own geometric structure. Recent theoretical work suggests that the answer might involve quantum decoherence operating on space-time itself. Just as ordinary quantum systems become classical through interaction with their environment, space-time might become classical through interaction with the matter and energy it contains. The presence of complex information processing systems like ourselves might play a subtle role in selecting which of the many possible quantum spacetimes becomes actualized as our experienced reality. This doesn't mean consciousness creates reality in any mystical sense. The process appears to be far more collective and physical than that. Rather, the existence of information processing systems throughout the universe might contribute to the emergence of stable classical spacetime through purely physical mechanisms involving quantum decoherence and error correction. Consider what this implies about the universe we inhabit. Reality might be engaged in a constant process of self-measurement, with every interaction between particles, every exchange of information, contributing to the ongoing construction of the space-time framework within which those very interactions occur. We exist within a cosmos that is continuously creating itself through the act of its own self-observation. As we venture further into these mysteries, we discover that the quantum nature of space-time creates profound puzzles about the relationship between memory, identity, and the flow of time itself. If space-time emerges from quantum information processing, then our conventional understanding of how memories connect us to the past must be fundamentally reconsidered. In classical physics, memory seems straightforward. Events occur at definite locations and times, leaving traces that can be stored and retrieved later. Your brain encodes information about past experiences, creating neural patterns that allow you to remember what happened, where and when. The past exists as a collection of facts about completed events. But in quantum space-time, this simple picture dissolves. If space and time are themselves quantum variables existing in superposition until measured, then the very notion of an event occurring at a definite location and time becomes problematic. How can information be stored about the where and when of an event if where and when don't have definite values until observed? This creates what we might call the quantum memory paradox. How can any system, whether a human brain or a cosmic information storage mechanism, preserve memories of past events if the space-time framework within which those events occurred is itself uncertain and fluctuating? Some speculative approaches to this puzzle suggest that memory might not be passive storage of information about fixed past events, but an active process that participates in the ongoing creation of the past itself. When you remember something, you might not be simply accessing stored data about predetermined historical facts. You could be participating in the quantum measurement process that gives definite meaning to past events. As you listen to this idea, pause and notice your own relationship with memory. Think about a childhood experience you recall clearly. From this quantum perspective, that memory might not be a simple recording of a fixed event that occurred years ago. It might be part of an ongoing process that helps to crystallize the uncertain quantum history into definite classical facts through the act of remembering itself. This doesn't mean memories are unreliable or that the past is entirely subjective. Rather, it suggests that the relationship between present memory and past events might be far more participatory and dynamic than we usually imagine. The act of remembering might be a form of quantum measurement that contributes to the ongoing construction of classical space-time from quantum foundations. This perspective also offers new insights into the nature of personal identity and continuity over time. If your memories participate in the ongoing construction of your personal past, then you're not simply a product of your history. You're an active participant in creating that history through the ongoing process of remembering and forgetting, attending and ignoring, weaving quantum possibilities into the definite narrative of your experienced life. One of the most remarkable aspects of quantum spacetime theories is how they explain the emergence of the familiar laws of physics from quantum foundations. The precise deterministic equations that govern the motion of planets, the behavior of light, and the flow of time itself might all be approximate descriptions that arise when quantum space-time effects average out over large scales. Think about how this transformation occurs. At the Planck scale, space-time is a churning foam of quantum uncertainty, where the very concepts of distance and duration lose their classical meaning. Virtual black holes pop in and out of existence. Causal relationships exist in superposition. The geometry of space fluctuates wildly from moment to moment. Yet somehow, as we zoom out to larger scales, this quantum chaos gives way to the smooth, predictable space-time described by Einstein's equations. It's like looking at a turbulent ocean from a great height. The individual waves, whirlpools, and foam become invisible, replaced by a smooth surface that appears calm and uniform. This emergence of classical physics from quantum foundations isn't just a mathematical curiosity. It reveals something profound about the nature of physical law itself. The equations we use to describe reality at human scales might not be fundamental truths about the universe, but rather statistical approximations that describe the average behavior of underlying quantum processes. Consider Newton's law of gravity, which describes how massive objects attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. This law works with extraordinary precision for everything from falling apples to orbiting planets. Yet from the perspective of quantum space-time, it might be an emergent phenomenon arising from the statistical behavior of quantum geometric fluctuations. The same might be true for all the fundamental constants of nature. The speed of light, the strength of the electromagnetic force, even the dimensionality of space itself, might not be fixed features of reality, but emergent properties that arise from the particular way quantum information organizes itself in our corner of the quantum multiverse. This perspective suggests that the laws of physics are not imposed on the universe from outside, but emerge from within through the collective behavior of quantum processes. The universe doesn't follow laws, it creates laws through its own self-organization and information processing. As you contemplate this idea, notice how it reframes your relationship to the physical world around you. The gravity that keeps you grounded, the electromagnetic forces that hold atoms together, the flow of time that carries you from moment to moment. All of these might be manifestations of deeper quantum processes that you participate in simply by existing. Earlier in our journey, we explored the holographic principle in the context of black hole physics and string theory. Now let's consider how this same principle might apply to conscious experience itself, offering new insights into the relationship between mind and the quantum universe. The holographic principle, you'll recall, suggests that all the information contained within a volume of space can be encoded on its two-dimensional boundary. Applied to black holes, this means that everything that falls into a black hole leaves its informational trace on the event horizon. The three-dimensional interior is completely described by information on the two-dimensional surface. Some researchers have speculated, though this remains highly controversial and unproven, that consciousness might exhibit similar holographic properties. Perhaps the rich three-dimensional experience of perceiving the world around you emerges from information processing occurring in lower dimensional neural networks in your brain. This is a speculative idea with no current experimental support, and most neuroscientists believe that consciousness arises from classical neural computation without requiring special quantum effects. However, the mathematical parallels are intriguing enough to warrant careful consideration. Consider how your visual experience works. your brain constructs a three-dimensional model of the world from two-dimensional patterns of light falling on your retinas. In some sense, your entire visual reality is a holographic projection created by information processing in your neural networks. The depth, volume, and spatial relationships you perceive don't exist in the sensory data itself, but emerge from sophisticated computational processes. This holographic quality of perception might reflect deeper principles about how information creates the experience of spatial relationships. Just as space-time geometry might emerge from patterns of quantum entanglement, the spatial structure of conscious experience might emerge from patterns of information correlation in neural networks. Take a moment to notice this holographic quality in your own experience right now. As you listen, you construct a sense of being located in space, of existing within a three-dimensional environment. Yet this spatial experience emerges from patterns of neural activity that don't themselves have the spatial properties you experience. Your brain creates space from non-spatial information processing. If consciousness does exhibit holographic properties, this might help explain some of its most puzzling features. How does the brain integrate information from different sensory modalities into a unified experience? How do you maintain a coherent sense of self despite the constant flux of thoughts, sensations, and memories? How does subjective experience arise from objective neural processes? While we don't yet have definitive answers to these questions, the holographic principle offers a conceptual framework for thinking about how higher dimensional experiences might emerge from lower dimensional information processing. It's a reminder that the relationship between information and experience, like the relationship between information and space-time, might be far more subtle and surprising than our intuition suggests. As our exploration continues, let's step back and consider the remarkable journey that has led from the quantum foam of the early universe to the emergence of conscious beings capable of contemplating their own quantum foundations. This cosmic evolution represents one of the most extraordinary developments in the history of reality itself. In the earliest moments after the Big Bang, when the universe was smaller than an atom and hotter than any star, space-time itself was dominated by quantum effects. The smooth geometry we experience today hadn't yet emerged from the quantum substrate. Instead, the cosmos was a seething foam of quantum possibilities, where space and time fluctuated wildly, and the very concepts of location and duration had no stable meaning. Yet somehow, from this quantum chaos, stable structures began to emerge. As the universe expanded and cooled, quantum fluctuations in the early cosmos provided the seeds for all future complexity. These tiny variations in density and temperature would eventually grow into galaxies, stars, planets, and ultimately into the complex information processing systems we call life. Consider the extraordinary chain of developments that led from quantum space-time fluctuations to your ability to contemplate quantum space-time. Quantum variations in the early universe led to the formation of the first stars. These stars forged heavy elements in their cores and distributed them through space when they exploded. These elements formed planets where complex chemistry could unfold. On at least one of these planets, chemistry became biology, biology became neurology, and neurology became consciousness. Now, billions of years later, patterns of quantum information that emerged in the first moments of cosmic time have evolved into information processing systems, sophisticated enough to investigate their own quantum origins. Through your consciousness, the universe has developed the capacity to study itself, to question its own foundations, to wonder about the nature of its own existence. This cosmic evolution of information processing might not be accidental. Some researchers have speculated, though this remains highly theoretical, that the universe might have inherent tendencies toward the development of complexity and consciousness. The same principles that govern the emergence of space-time from quantum information might also govern the emergence of life and mind from simpler physical processes. As you listen to these ideas, take a moment to appreciate your place in this cosmic story. You are not an accidental byproduct of meaningless physical processes. You are the universe's way of understanding itself, a temporary but remarkable concentration of the cosmic information processing capacity that creates and maintains all of reality. So here we are, having travelled from the smallest possible scale in the universe to the grandest questions about the nature of existence itself. We began by asking a seemingly simple question. At what point does space-time become quantum? What we discovered is that this question opens like a flower into some of the most profound mysteries about reality, consciousness, and our place in the cosmic dance of information and geometry. The answer, as we've seen, is both precise and beautifully ambiguous. Space-time becomes quantum at the Planck scale, where quantum uncertainty begins to affect the very fabric of space and time. But the deeper truth we've uncovered is that space-time is always quantum, even here, even now, as you listen to these words. The smooth, continuous reality we experience emerges from quantum foundations, like a symphony arising from individual notes. We've glimpsed a universe where space and time are not the rigid stage upon which existence unfolds, but dynamic, emergent properties of something far more fundamental, the processing of quantum information itself. Every breath you take, every thought that crosses your mind, every moment of awareness participates in the vast cosmic computation that maintains the space-time framework within which all existence dances. This isn't mysticism masquerading as science. It's mathematics revealing poetry, rigorous physics uncovering beauty. The universe we've explored tonight is stranger than our ancestors imagined, yet it's also the same cosmos we've always inhabited. We're simply learning to see it with new eyes, to recognize the quantum foundations that have always hummed beneath the surface of classical experience. As you return to your daily life, carrying these ideas with you like seeds of wonder, remember that the ordinary experiences